and today we are starting with transformation of the gamma function. That is, apart from the definition that I have given to you, that is the definition of gamma of n will be equal to integral from 0 to infinity raised to power minus t raised to power n minus 1 ds. So there are also different ways we can write the gamma function, as you can see here. So we have 4 different forms of the transformation of the gamma function, and we are going to be proving them in this video. So we come to the first one, from 1. We want to prove that the gamma function of n is equal to 1 over n integral from 0 to infinity of e raised to power minus s raised to power 1 over n ds. The first thing I'm going to do here is I can start from the right hand side and prove this, or I start from the left hand side and prove this. Now I'll say let, from here, I'm starting from here, let t be equals to s raised to the power of 1 over n. That's the first thing I'm going to do. Let t be equal to s raised to the power of 1 over n. It means that s will be equal to t raised to power n. S will be equal to t raised to power of n. Then differentiate the s is equal to nt raised to the power of n minus 1 dt. That's what I'm going to have. The s equal nt raised to the power of n minus 1 dt. The next thing that will happen is that I'll substitute. Of course, when s is 0, t is 0, and when s is infinity, t is also infinity. So it means that I have 1 over n, this is what I have at the left hand side, integral from 0 to infinity of e raised to power minus s raised to power 1 over n ds is equal to 1 over n integral from 0 to infinity of e raised to the power of minus s raised to the power of 1 over n is t. S raised to the power of 1 over n is t. So that means I have e raised to power minus t multiplied by ds, and ds I have here, ds is equal to nt n minus 1 dt. So multiplied by nt n minus 1 dt. So the n can come out. When the n come out, it divides this n, so that I will be left with integral from 0 to infinity of e raised to power minus t raised to power n minus 1 dt. And that is exactly gamma of n. So this is equal to gamma of n. So that's what I have. So I'm done with number 1. Therefore, gamma of n is equal to the integral from 0 to infinity of e raised to power of, is equal to 1 over n integral from 0 to infinity e raised to power minus s raised to power 1 over n ds. So the next one is number 2. I want to prove 2. So to prove 2, I have gamma of n to be equal, to conclude that one, we have in particular integral from 0 to infinity of e raised to power minus s squared ds equal root pi over 2. So what is that trying to say? From here, from 1, you let n to be 1 over 2. Now put n to be 1 over 2, so that we have gamma of 1 over 2 to be equal to 1 divided 1 over 2 integral from 0 to infinity of e raised to power minus s. 1 over n is 1 divided 1 over 2, that is 2. So that's why I have e raised to the power of minus s squared. This is square root of pi, and all this one will give me 2 from 0 from integral from 0 to infinity of this. So divide both side by 2, you will get what we have. integral from 0 to infinity of e raised to power minus s squared ds will be equal to root pi all over 2. So now the next one, 2, the second one, number 2, we have gamma of n to be equal to k raised to power n integral from 0 to infinity of e raised to the power of minus ks s raised to the power of n minus 1 ds, where n and k are greater than 0. So I want to prove this as well. In this case, I'll also start from the right hand side. I will say let t be equal to ks. Let t be equal to ks. I can just make s the subject of formula. I have t over k. That is what I'm going to have. Then I differentiate. The s will be equal to 1 over k dt. So don't forget, when s is 0, t is also 0. When s is infinity, t will also be infinity. So I have I have this k raised to power n integral from 0 to infinity of e raised to power minus ks s raised to power n minus 1 ds is equal to, this is still k raised to power n integral from 0 to infinity e raised to the power of minus t, because I've given the substitution that ks to be equal to t. So e raised to the power of minus t, s is t over k, so I have open bracket t over k raised to the power of n minus 1 multiplied by the s. The s is 1 over k dt. 1 over k dt. So this will become k raised to the power of n integral of 0 to infinity. This will be e raised to the power of minus t. This is t raised to the power of n minus 1 over kn minus 1 multiplied by another k. It will give me exactly k raised to the power of n dt. And this will be equal to, the k raised to the power n is a constant. It will come out. It will divide this as well. This one will become exactly integral from 0 to infinity e raised to the power of minus t, t raised to the power of n minus 1 dt. So I have this, and this is exactly gamma of n. So this is exactly gamma of n. That's exactly gamma of n. So at the end of the day, I have at the end of the day, we can see that gamma of n also can be written as k raised to the power of n integral from 0 to infinity e raised to the power of minus ks s raised to the power of n minus 1 ds. That's what I'm going to have. So in practice, when we want to integrate this integral from 0 to infinity of e raised to the power minus ks s raised to the power n minus 1 ds, whenever we have an integral of this form and we want to compute the value or the sum, this will be equal to gamma of n all over k raised to the power n. Of course, I just took I divided both sides by k raised to the power of n, and that's what we are going to have. Now let's move to form 3. Form 3 is saying that gamma of n, that's what we want to prove, is equal to integral from 0 to 1 of log 1 over s raised to the power of n minus 1 ds, and n is greater than 0. So that is the third thing we are going to do. Now I'll start from the left hand side. I'll start from the left hand side of the equation. Again, here you will let t be equal to log of 1 over s. Of course, you will notice what I'm trying to do. In this case, for instance, in this previous example, just look at it. the gamma function is given as integral from e raised to power 0 to infinity of e raised to power minus t raised to power n minus 1 dt. So your aim is to express or have a form like this, e raised to power of minus t. So when you have e raised to power minus ks, let t be that ks. So in this case as well, I can see what I have. I let t to be log of 1 over x, and you will see what it will eventually become. T is equal to, this is minus log s. Don't forget, 1 over x is x raised to the power of minus 1. And since I'm talking about logarithm, the minus one will come to the will come forward to become minus log s, and you can transfer it. This one will become minus t is equal to log s. You can have this as Now the next thing is to find s. In reality, what I'm trying to do here is I want to make s the subject. So I now differentiate. The s is equal to minus e raised to power minus t dt. That's what I'm going to have. So I substitute into the right hand side, or what I have at the right hand side, our integral. So I have our integral from 0 to 1. Okay, before I continue, when s is 0, now I have this t equal log 1 over s, or you say minus log s. When s is 0, t will be equal to what? Minus log 0. Log 0 is negative infinity because e raised to the power of minus infinity is 0. So if I take the ln of both sides, or the logarithm of both sides, this one will be minus infinity equals 0. So negative infinity is log 0. So, and I have negative in front, so t will be infinity. So when s is equal to 1, when you put 1 here, that is log 1, minus log 1. And t, when s is equal to 1, I have log 1. Log 1 is 0. Log 1 is 0. So that's all. So I will now substitute. I have integral from 0 to 1 of log 1 over s raised to the power of n minus 1 ds. This will become integral. So I will change the bound as well. This one will become infinity, while this one will become 0. Log of 1 over s is t. Log of 1 over s is t. So that's t raised to the power of n minus 1 ds. ds is minus e raised to power minus t dt. So multiply by minus e raised to power minus t dt. So I swap the integral. When I swap the integral, I will take away negative. I swap the bound rather. As I will swap the bound, that will become from 0 to infinity. Then this negative will be out, or you put another negative outside. And when you put another negative outside, negative times negative will give you positive. So you'll be left with t raised to the power of n minus 1 e raised to power minus t dt. And this one is exactly the gamma of n. And we are true. So that means, therefore, gamma of n is equal to integral from 0 to 1 of log 1 over s raised to the power of n minus 1 ds. So then I go to the last one, number 4, the last transformation. So for the last transformation, I have gamma of n to be equal to 2 integral from 0 to infinity of e raised to the power of minus s squared x raised to the power of 2n minus 1 ds. Yes, this is also another trivial proof. So we let x, of course, let the radar to be equal to s squared. I told you this is what you should watch, e raised to the power of minus t. So let t be equal to s squared, then differentiate. The t will be 2s dx. So I can make the s the subject. The s will actually be equal to 1 over 2s dt. That is what I'm going to have. But what is x? If we make s the subject of formula here, s will just be square root of t. S will just be equal to the root of t, or t raised to the power of 1 over 2. So the s is 1 over 2t raised to the power of 1 over 2 dt. That is what I'm going to have. So I have gamma. I have 2 integral from 0 to infinity. I have 2 integral from 0 to infinity of e raised to the power of minus s squared, s raised to the power 2n minus 1 ds, to be equal to 2. Don't forget, when x is 0, t is 0. When x is infinity, t is infinity. So integral from 0 to infinity of e raised to the power of minus t, because a squared is now t. So I have e raised to the power of minus t multiplied by s. S is t raised to the power of 1 over 2. S is t raised to the power of 1 over 2. So I have t raised to the power of 1 over 2. Then this 2n minus 1 is still there. I will put it 2n minus 1 ds. So ds will be multiplied by, I'm going to write it below, 1 over 2 t raised to the power of 1 over 2 dt. So this is what I'm going to obtain. I will have 2 integral from 0 to infinity e raised to the power of minus t, t raised to the power of 1 over 2 times 2n will give me n, minus 1 over 2. Multiply by, then I have 1 over 2 t raised to the power of 1 over 2 dt. That is what I'm going to have now. So the next thing that will follow is this 2 will come out. It's a constant. It will divide this 2. That will be out. So I will be left with integral from 0 to infinity of e raised to the power of minus t. Then I have this t raised to the power of n minus 1 over 2. Then this is also t raised to the power of 1 over 2. When it comes up, it becomes t raised to the power of negative 1 over 2. And from law of indices, I can also add it this way, the t. So I have n minus 1 over 2, this t, 1 over t, 1 all over t raised to the power of 1 over 2 is t raised to the power of negative 1 over 2. And from law of indices, when two things are multiplying with the same base, you can add the powers. And that's what I've done here. So I have, at the end of the day, integral from 0 to infinity of e raised to the power of minus t, t raised to the power of n minus 1 dt. And this is just gamma of n. Therefore, gamma of n is equal to 2 integral from 0 to infinity of e raised to the power of minus s squared, s raised to the power of 2n minus 1 dx. So we have concluded the different form of writing the gamma function, the transformation of writing the gamma functions. You have seen them now. So the next thing I'm going to do, let us look at some examples. Let's look at some examples here. So we want to do this, show that the integral from 0 to 1 of s raised to the power of n minus 1 log 1 over s raised to the power of n minus 1 ds is equal to gamma of m all over n raised to the power m. Number 2, integral from 0 to 1 of s raised to the power m log s raised to the power n dx is equal to minus 1 raised to the power n and factorial all over n plus 1 raised to the power of n plus 1. Then number 3, show that integral from 0 to infinity of x raised to the power c all over c raised to the power s dx equal gamma of c plus 1 all over log c raised to the power of c plus 1, where c is greater than 0 as well. Then this last one, compute integral from 0 to infinity of 3 raised to the power of minus 4s squared ds. That is what we want to do. So number 1, integral from 0 to 1 of s raised to the power of n minus 1 of log 1 over s raised to the power of n minus 1 ds. So this is what I'm going to do. I will let t to be equal to 1 over x. Let t to be equal to log 1 over s. You make s the subject. This one will be t equal minus log s, and when by the time you make s the subject of formula, you will get s to be equal to e raised to the power of minus t. Differentiate. ds is equal to minus e raised to the power of minus t dt. That's what you are going to have. Then next is you are going to talk about the bound when s is 0. When s is 0, you have t to be infinity. This is minus log s. T equal log of 1 over s. This is s raised to the power of minus 1. Why the minus can come here? Minus log s. So when s is 0, this t will be infinity. When s is 0, t will be infinity, because log of 0 is negative infinity. Multiplied by another negative, you have infinity. And when s is 1, log 1 is 0. So t will be 0 as well. So you have integral from 0 to 1 of s raised to the power of n minus 1 log 1 over s raised to the power of n minus 1 ds to be equal to integral from infinity to 0. That's what it will become. Infinity to 0, s is e raised to the power of negative t. So I have e raised to the power of minus t. Then you will now multiply it with n minus 1. I have n minus 1 here, right? Then this one will be log of 1 over s is t. Log of 1 over s is t. I have t raised to the power of n minus 1. N minus 1 ds. ds is negative e raised to the power minus t dt. So multiply by e raised to the power of negative e raised to the power of negative t dt. That's what I'm going to have. So now I'll swap the bound. This bound become integral from 0 to infinity of, I have t raised to the power of n minus 1. This will become, let us be explicit, this negative will be out because I have swapped the bound to become 0 to infinity. This one will become e raised to the power of minus tn plus t, right? Then another one is here again, minus t. So minus t, that's what I'm going to have. So after that, I have t raised to the power of m minus 1 the t. So that is what we are going to get. So this one will become integral from 0 to infinity. Integral from 0 to infinity of e raised to the power of minus tn multiplied by, so I have integral from 0 to infinity raised to the power of minus tn, because t minus t will give me 0, of t raised to the power of n minus 1 dt. So that's what I'm going to have. So the next thing is I will actually use this form 2 to solve the rest. I'm going to use this form 2 to complete this question. And don't forget, I told you before now that after I go from form 2, I told you that I can write integral from 0 to infinity of e raised to the power of negative k s raised to the power of n minus 1 ds to be equal to gamma of n all over k raised to the power of n. So integral from 0 to infinity raised to the power of minus ks s raised to the power of n minus 1 ds will be equal to gamma of n kn. If you look at what I have here, if you replace k with n and n with m, so it means that if I replace k with n, I will have e raised to the power of minus ns. That's what I'm going to have. And if I replace n with m, I have s raised to the power of n minus 1 ds. This will be equal to gamma of n, but I have replaced n with m, so I have gamma of m all over k. This is k, I have replaced it with n, so I have n raised to power n. N is m here, so I have this. So you can check this very well. What I have just done here is I replace k with n, so that means this one will be n. I replace n with m, so this will be m, and this n will also be m rather. So that means this one, according to from 2 of what we have done before now, is equal to gamma of m all over n raised to the power of n. And that's all. We are done with number 1. That is the proof of number 1. Now let's go to number 2. Let's go to number 2 proof. So number 2 is saying that integral from 0 to 1 of s raised to the power m log s raised to the power of n dx. In this case, I will let t to be equal, or I say let negative t to be equal to log s. Why did I put negative t? I put negative t because this is not 1 over s. It's not log of 1 over s. So I put negative t so that by the time I make s the subject of formula, I have e raised to the power of negative t. So by the time I make s the subject, I obviously have e raised to the power of negative t. Don't forget, then differentiate ds is equal to negative e raised to the power minus t dt. That's what I'm going to have. Of course, you now know the logic. When s is 0, t is infinity. When s is 1, t is 0. So I have this one, integral from 0 to 1 of s raised to the power n log s raised to the power n ds will now be equal to integral from infinity to 0 of s is e raised to the power minus t, so raised to the power n. This one will become e raised to the power minus nt log s. Log s is negative t, so I have negative t raised to the power n multiplied by ds. ds is negative e raised to the power minus t dt. Negative e raised to the power of minus t dt. So that at the end of the day, I can swap the bound and take away this negative. This one will become integral from 0 to infinity of e raised to the power of minus mt. This one will give me minus 1 raised to the power n t raised to the power of n as well, minus 1 raised to the power n, t raised to the power of n, then multiply by e raised to the power of minus t dt. So minus 1 raised to the power n can come out of the integral. Minus 1 raised to the power n can come out. I have this. At the end of the day, I will have an integral from 0 to infinity of e raised to the power of, this is minus mt minus t. If I factorize the minus, I will have minus m plus 1 t. That's what I'm going to have. This is e raised to the power of minus mt minus t. Factorize minus, you have mt plus t, then factorize t, you have minus m plus 1 t. Then I have t raised to the power of n dt. So according to this as well, if you look at this very well, I'm still using from 2. From 2, here my k will be n plus 1. My k will be n plus 1, and this n will be n plus 1 minus 1, because this is actually, this n is actually n plus 1 minus 1. This n is n plus 1 minus 1 actually. So that's what I have here. So I have, so this one will now be from 2, this one will be equal to gamma of n plus 1, because it is gamma of n when you have n minus 1. So when you have n, it is n plus 1 minus 1. So that is gamma of n plus 1 all over n raised to the power of n. What is n here? N is n plus 1. Don't forget, I have n plus 1 raised to the power of, what is here? Minus ks. The k here is n plus 1. So I have n plus 1 here. That's what I have. So from that, I have used this from 2 again. Just look at it closely. You will get what I'm trying to say. Whatever is beside exponential minus the constant that is beside k before the s will be at the denominator. And the s raised to power n will be gamma of n, and it will also raise to the power of what is beside the s at the denominator as well. So I have this, and then don't forget gamma of n plus 1 is n factorial. I've done that in the first video. So this is minus 1 raised to power n. Gamma of n plus 1 is n factorial. So I have n factorial all over n plus 1 raised to the power of n plus 1. Of course, n has to be a positive integer before this can hold, or before you can talk about the factorial. So that's what I have. Then I want to go to the next one, number 3. Number 3 as well. Let's go to number 3. Number 3 is saying that we should show that integral from 0 to infinity of s raised to power c over c raised to power s ds is equal to gamma of c plus 1 all over log c raised to the power of c plus 1. So this is actually equal to integral from 0 to infinity. Look at what I'm going to do. Of c raised to the power of negative s. This is c raised to power s at the denominator. It becomes c raised to the power of negative s. Then s raised to the power of c ds. So I will do something now. This is integral from 0 to infinity. This c raised to the power of negative s, I can write it this way. I can write it as e raised to the power of log c raised to the power of x multiplied by s raised to the power c ds. This is the first thing you have to note here. You have to note that whenever you have a raised to the power of log to base a, whenever you have a raised to the power of log to base a, Whatever may be here will be the answer. This is part of the law of logarithm. A raised to the power of log base A, then you have n, the answer will be n. You can check for any value, you can try it. So this is what we have. Again, so in this case, this is e raised to the power of log base e. Since I have, when I don't write anything there, the base is e, the natural, the exponential, the Euler number. So e raised to the power of log base e of c raised to the power of minus s, I don't need to write e, is equal to what is here, c raised to the power of minus s. So that's what we have. So that's what we have. That's why we have the e raised to the power of log c raised to the power of minus s, according to this law of logarithm. So then I will have, since this is power and this is log, this one will be equal to integral from 0 to infinity of e raised to the power of, this is minus x log c. That's what I'm going to have. Then I have s raised to the power c ds. I have x raised to the power c ds. I can also write this way, integral from 0 to infinity of e raised to the power of minus, then I decide to write log c first, multiply by s. It's still the same thing. Whether you put s at the back here or you put it here, just make sure it's not inside the log. It's still the same thing. So I have s raised to the power c ds. So now, again, I just applied it from two of these, of the transformation of the gamma function. Look at it. I told you that from 2 can also be written this way, integral from 0 to infinity. That is, if you divide both sides by k raised to power n, you have integral from 0 to infinity of all these things, all this integral to be equal to gamma of n over k raised to power n. So to get this, look at what I'm going to do. Let this k be equal to log c. Let k be equal to log c, and let n be equal to c plus 1. Let n be equal to c plus 1. So replace it here. Of course, I'm coming from 2. This is just from 2. I have just rewritten from 2. Then replace this. Anywhere you see k, put log to base c, log c. Anywhere you see n, put c plus 1. So this will become integral from 0 to infinity of e raised to the power of minus k. But I said let k be log c. That will be log c. Then I have s. Multiply by s raised to the power of n. Don't forget I said let n be c plus 1. So put it there. C plus 1 minus 1. C plus 1 minus 1 will give me c. So I will just be having s raised to the power c ds. And that will be equal to gamma of n. N is c plus 1. That's gamma of c plus 1 all over k. K is log to base c, log c. So I will have log c here, raised to power n, raised to power c plus 1. So that means all these ones is equal to this. If you look at what I have here at the left hand side of the integral, that's what I have there. So this one will be equal to gamma of c plus 1 all over log c raised to power c plus 1. And that will be the answer for this number 3. For this question 3, that will be the answer. Now, lastly, let's do the last one. Number 4. Compute. We are told to compute, that is, we have to find this integral from 0 to infinity of 3 raised to the power of minus 4s squared dx. We want to compute this, we want to find the integral of this. So look at what I'm going to do. I'll let t to be equal to s squared. That is the first thing I'm going to do. Make s the subject, s to be equal to t raised to the power of 1 over 2. So differentiate. The s is equal to 1 over 2t raised to the power of minus 1 over 2 the t. When you differentiate, that's what we are going to have. So put it there, put it in the integral. When s is 0, t will be 0. When s is infinity, t will also be infinity. So I have this one will become integral from 0 to infinity of t raised to the power of minus 4t, because s squared has now been replaced with t. Minus 4t multiplied by ds. ds is 1 over 2 t raised to the power of minus 1 over 2 the t. That's what I'm going to have. So this one will be equal to 1 over 2 can come out. 1 over 2 integral from 0 to infinity of t raised to the power of minus 1 over 2, then t raised to the power of minus 4t the t. That's what I'm going to have now. So this will become 1 over 2 integral from 0 to infinity of t raised to the power of minus 1 over 2. Then this one, what I did for this number 3, I will do the same for this one as well. This one is exactly e raised to the power of log of 3 raised to the power of minus 40 dt rather. So I have 1 over 2 integral from 0 to infinity. That's what I have. 1 over 2 integral from 0 to infinity of t raised to the power of minus 1 over 2. That's what I have. Then this minus 40 can come to the back, can come to the front of the logarithm. I have e raised to the power of minus 40 log 3 dt. That is what I'm going to have. So to complete that one, to complete that question, we have next 1 over 2 integral from 0 to infinity of t raised to the power of minus 1 over 2. Then I can rewrite all this that I have there to be minus 4 log 3. That's minus 4 log 3 t dt. That's what I'm going to have. So again, I will use this from 2. From 2 has been helpful in all the exercise I have written today. So now, this is, of course, you can see, it's obvious, this is our k now. K will be 4 log 3 and our n will be what? Let's look at it. So in this case again, let k, this is what we are going to use to substitute now. Let k, you put k to be 4 log 3. 4 log 3, and you put n to be 1 over 2. When you put n to be 1 over 2, when you put n to be 1 over 2, this one will become integral from 0 to infinity of e raised to the power of minus k. K is 4 log 3. So that's 4 log 3 s raised to the power of 1 over 2 minus 1. N is 1 over 2. That's 1 over 2 minus 1. So I have 1 over 2 minus 1 will give me minus 1 over 2. The s will be equal to gamma of n. N is 1 over 2. Don't forget, I'm just substituting 1 over 2 all over k raised to the power of n. K is 4 log 3. 4 log 3 raised to the power n. That's raised to the power of 1 over 2. So now that's what I'm going to have. So that means all this I have here, this one is equal to 1 over 2. 1 over 2. Then the answer to this integral is equal to gamma of 1 over 2 all over square root of 4 log 3. So this is 1 over 2 Gamma of 1 over 2 is root pi all over root of 4 is 2, so I have 2 roots log 3. So the answer is root pi all over 4 square root of log 3. That's the answer. That's the answer to that question. So I think that's all.